Hello, and thank you for watching our critical design review. This is Group 18, the smart locking and tracking system for bicycles, also known as Sentry. Our team is comprised of 4 members: Andres Garcia, Derek Amin, Russell Ridley, and myself, Ryan Baumgartner. Together, we are 2 electrical engineering majors and 2 computer engineering majors.
One of the biggest challenges on university campuses is bike theft. Many students rely on bikes as their primary mode of transportation, but unfortunately, bike theft is a recurring issue that makes people hesitant to use them. This isn't just about the loss of a bike, it disrupts daily routines. If a student's bike is stolen, they might be late for class, have to find an alternative mode of transportation, or even avoid biking altogether in the future, which affects sustainable transportation habits. Right now, traditional bike locks don't provide proactive security. They only act as a physical barrier, but if someone cuts the lock, the owner has no idea until they return and find their bike missing. There's no immediate alert, no tracking system, and no way to recover the stolen bike quickly. But with advances in IoT and smart technology, we can change this. We now have the ability to integrate real time alerts, GPS tracking, and remote monitoring, making bike security much more effective. That's where our smart bike lock, Sentry, comes in, providing a smarter and more secure way to protect bikes. Sentry is a high-tech bike locking and tracking system designed to provide both security and convenience. It features NFC and BLE for secure unlocking, allowing users to tap their phone or use the mobile app. GPS tracking enables real-time location monitoring, helping users track their bike if it's moved or stolen. With cellular connectivity, the system sends instant alerts when tampering is detected, ensuring owners are notified immediately. An audible alarm deters theft by drawing attention, while the mobile app provides full control over unlocking, tracking, and security notifications. By combining these smart technologies, Sentry offers a proactive approach to bike security, making theft prevention and recovery more effective. The primary goal of Sentry is to enhance bike security using NFC, GPS, and cellular connectivity. It prevents theft through tamper detection, audible alarms, and instant alerts, while real-time GPS tracking assists in biking recovery. A user-friendly mobile app allows for tracking, unlocking, and monitoring, ensuring ease of use. The system is designed with durability and outdoor resilience in mind. For our advanced goals, we want to provide real-time battery monitoring, multi-user access, geofencing alerts, and automatic locking after a period of time. Future stretch goals involve bike usage analytics, a physical key backup, and solar charging to extend battery life. These features ensure a robust, smart, and adaptable bike security system.
The Sentry hardware design consists of 2 main subsystems, the locking system and the tracking system, both of which work together to kind of help us achieve our goals. The locking system has multiple PCBs, starting with the main PCB itself, which houses the MCU and the BLE module for communication. Um, Moving on to the motor controller PCB, which drives the locking mechanism, and the NFC antenna and matching circuit PCB, which helps us unlock and lock the bike via NFC. Additionally, we have the 3.3 and 5-volt regulator boards PCBs to ensure proper power distribution across the system. The communication with the locking system is done through the BLE module, and it also uses the antenna, which also facilitates any external communication. The tracking system itself is the one that's responsible for real-time monitoring of the bike and any theft prevention. So it's all on one PCB, which includes the MCU with LTE capabilities for us to track the bike for a long range, as well as a BLE module for any short-range communication. It also includes a alarm in case there's any tampering or anything like that. And all of these things connect to a database, which is connected to our mobile application, where the users actually interact with the lock itself through the application. The app itself provides real-time location updates, the lock status, and any alerts in the event of any tampering and things like that. So in order to meet our goals, we needed to define the required specifications. The reason behind this is that we need to have set parameters of the goals that we want to achieve with our system. Since the product is going to be used on a daily basis by students, we want a refined product that the students can trust and still be in charge of keeping the bikes safe and secure. So with the locking system and the tracking system, as you can see, those are the specifications. Um, in the locking system, we're prioritizing the response times because we want to make sure that as soon as the user taps the lock with the NFC tag, one, that it doesn't take too long to unlock the bike. It's within a few seconds. And two, the near field, the NFC distance is relatively small. And so for the tracking system itself, the specifications that we wanted to highlight and show in our case are the GPS accuracy. And the reason behind our selection is that the product needs to excel in this area because in case the user is not able to find the bike, or if the bike has been stolen, they can use the application to track the location of the bike.
To control our two main PCBs, we first needed to choose between microcontrollers and FPGAs. While FPGAs have high performance power and scalability, our main concerns with this project were low power consumption and ease of integration, since 1, the systems will be powered by batteries, and 2, different components can be integrated together much more easily with microcontrollers. That is why for this project, we have chosen to go with MCUs over FPGAs. We compared several on-the-market MCUs, and after analyzing factors like cost, power consumption, and operating temperature, as well as peripherals like Bluetooth and LTE, we chose 2 different MCUs. For our locking system, we have chosen to use an ESP32. This microcontroller consumes very little power and is very low cost. It has several GPIO pins and can interface with the main embedded wired communication protocols. The form factor of this chip also allows us to be able to easily solder it to the PCB. For the tracking system, we have chosen to use the Maker MB1500 from our Arduino. We have chosen this board mainly due to its built-in cellular service, allowing us to connect to the LTE network. Having LTE built into the device means not having to worry about configuring external modules, which will make the cellular tasks easier as well. It is also important to note that this board is the most expensive of the boards we compared. We do believe, however, that in this situation, reliability is everything, and paying more for this board would save us more in the long run. Given that this board is also built by Arduino, there is a vast ecosystem that allows us to integrate with existing libraries seamlessly, making it the best solution for the task of tracking.
For our stepper motor, we compared 3 different sizes, NEMA 8, 17, and 23. The NEMA 8 was the best due to its small size, lowest current rating, and lowest weight. To pair the NEMA 8 stepper motor, we also require a stepper motor driver. Between the 4 drives, we picked the TMC2208 since it gives us the ability for 1/256 microsteps, allowing us to have the max control for our locking mechanism.
For our short-range communication with the bike lock, we chose NFC. NFC is the better choice for our smart bike lock due to its short range, security, and smartphone integration. With a 10cm range, NFC ensures only the owner can unlock the bike, unlike RFID, which operates up to 100 meters and is more vulnerable to unauthorized access. NFC is also cheaper, more intuitive, and consumes less power, which makes it ideal for a battery-powered lock. Unlike RFID, NFC supports bidirectional communication, allowing secure authentication between the lock and the phone. Most importantly, NFC works with smartphones, enabling seamless unlocking without extra hardware. These factors make NFC the best fit for Sentry security and ease of use. For our NFC controller, we chose the Adafruit PN532 due to its cost effectiveness, multiple interface options, and compatibility with our system. It supports UART, SPI, and I2C, allowing flexibility in communication with the ESP32. While its data transfer rate is lower than other options, it is sufficient for our use case. The integrated antenna simplifies implementation, and its 3.3 volt to 5 volt operating range ensures compatibility with our hardware. Most importantly, at 92 cents, it is significantly more affordable than alternatives like the Seed Studio NFC Shield and DF Robot Gravity Module, making it the best choice for our budget without sacrificing essential functionality.
As mentioned earlier, long-range communication is important for a project like this, as the two systems need to be able to talk wirelessly with each other. For internal communication between the devices, we have chosen to use Bluetooth Low Energy, as it is a fast protocol with very little power consumption, even less than standard Bluetooth. While devices will still need to be relatively close in order for the communication to happen, this is okay for us, since if the two devices are not close to each other, it is more than likely someone has stolen the bike anyways. Discussed earlier as well, we have chosen to use LTE-M. This protocol runs on the same framework as LTE, allowing for easy integration between the two. Using LTE-M allows us to not only send and receive data from the database, but also allows us to send text messages to the user, alerting them of a robbery in progress. Since LTE is built into the Maker board, that leaves finding a module for Bluetooth. After research, we found 4 popular BLE boards. After comparing factors like interfacing, ease of integration, and cost, we decided on the HM10. The HM10 is a very popular board for BLE and can easily be interfaced with using UART or SPI. Attention or AT commands are used to set up and program the board, and an IDE easily allows for the automation of sending these commands. The module also has non-volatile memory, meaning setup is not required every time the board receives power. For this application, we believe the HM10 is perfect for allowing communication between the ESP32 and the tracker.
For our tracking system, GPS was the best choice due to its global coverage and high accuracy, making it ideal for outdoor bike tracking. While WPS, also known as Wi-Fi Positioning System, is cost-effective, it relies on Wi-Fi network availability, which is unreliable in outdoor environments. BLE can be used for short-range tracking, but requires a dense deployment of beacons, making it impractical for our use case. For our tracking system, we selected the U-Blox SAM M8Q due to its high sensitivity, low power consumption, and straightforward integration. It supports both UART and I2C interfaces, making it flexible for communication with our microcontroller. While the Adafruit Ultimate GPS is a viable option, it only offers standard GPS accuracy, whereas the SAM M8AQ provides better sensitivity for improved tracking.
Since our tracking system will also have an alarm system, some sort of sound device is necessary to produce a loud enough sound to not only deter a thief in progress, but also alert others nearby of the potential robbery. The two main contenders for sound production were buzzers and speakers. While speakers are more dynamic, meaning they have better audio quality and frequency range, they also can consume a lot of power and for our application would more or less be overkill. For these reasons, we have chosen to use buzzers as they can provide enough volume as speakers can, with better size and cost, as well as better power consumption. While there are many different buzzers on the market, sound pressure level ratings are one of the key considerations when picking the right buzzer. Since the maker board can provide 5 volts out, it would be best to use this voltage rather than something larger. However, many buzzers compared here and on the market do not provide a very high SPL for 5 volts. For example, most buzzers can produce levels of 110 dB or higher, but require more than 12 volts. Luckily, after browsing online for a while, we came across the 2429 TWT from PUI Audio. At a rating of 98 dB at 5 volts, this buzzer will be able to provide just enough volume outside so that anyone in a close enough range to the bicycle will be able to hear it.
In this slide, you can see different components that make up our systems and their voltage, current, and power requirements. On the left, we have the tracking system, and on the right, we have the locking system. Please note that these values are due to change since not all the components will draw max power all the time. For example, our motor will only draw power when the user requests to unlock and lock the shackle. Knowing our power requirements, we can now select a battery. To keep things simple, both systems will use the same battery. For our selection, we chose lithium-ion batteries, since it's a smaller battery, has a higher efficiency, and a low discharge rate when not in use. From there, we selected the 3.7 10,000 mAh battery due to it having the longest capacity and allowing the user to use our product for longer periods of time. For our locking system, we required 2 different voltage regulators, a 3.3 buck converter to drop the voltage from 5 volt to 3.3, and a boost regulator for the 3.7 to 5 volt. The most important factors for selecting each regulator was its efficiency, size, and component total. The reason behind these factors, we wanted a regulator that's easy to solder, lowest component total to keep the complexity down, and the efficiency so we get the best power. From there, we selected the TPS 613221 and the MT3068. In this slide, you can see the block diagram of our locking system, from the 3.7 battery, the charger, 5 volt regulator, motor controller, motor, MCU, 3.3 regulator, and the NFC. In this slide, you can see the overall schematics from the ESP32, motor controller, UART bridge, buck converter for the ESP32, NFC controller, 5 volt boost converter, NFC antenna, the 3.3 buck converter, and the USB port. It should be noted that we are using the AMS1117 voltage regulator, which is usually found on the ESP32 dev board. This is our main PCB for our locking system. The board is separated, the NFC on the left and the ESP32 and the CP21 on the right. Currently, the NFC and the ESP are not connected with traces, so we can test each system independently so that once the issues are ironed out, we will connect them with traces. In this slide, you can see our motor controller and NFC antenna PCBs. Both are separated on their own boards so we can fine-tune each board independently, or if we run in the case where our stepper driver burns out, we are able to replace the board completely without damaging our main PCB. To cap off the locking system PCBs, we have the 3.3 and the 5 volt regulators, as well as separate boards, so that, as similar to the motor driver, if they burn out, we can replace the PCBs without messing up our main PCB.
Here is a simplified block diagram for the hardware of the tracking system. We can see that the 3.7 volt lithium polymer battery will be connected directly to the maker board, making it simple for powering the board and easy for us to monitor. The microcontroller will power and control the Bluetooth module, the GPS module, and the buzzer simultaneously. Overall, this design is fairly simple, but crucial to making the entire product work properly. The overall schematic for the tracking system can be seen here. On the top left, we have the pin headers for the maker board, and to the left of that, there is a voltage divider allowing us the ability to measure the life of the battery, which is connected to the board directly. On the top right, we can see a simple circuit used for the buzzer alarm. On the bottom left is the HM10 module, which we are connecting through UART, and on the bottom right is the Sarah M8Q, which we are connecting through I2C. This is the PCB layout of the tracking system. On the left is the current version 1 of the board with the external LTE antenna connected. While the current design works properly, we have made a slight redesign of the board seen on the right. In this version, we included the ADC for the battery that was left out before, and also removed an additional wire trace that was accidentally included in our previous iteration, which shorted a few other wires to ground. We are planning to purchase this board very shortly and move over everything to that PCB in the following days.
After covering electronics, we move on to our enclosure and shackle, which will be custom made by us. Our material of choice is PETG for our enclosures due to its low cost and good tensile strength. For our shackle, we chose aluminum for its low weight. Here you can see our lock base, which will house our PCB, our battery, and hold our motor, as well allow the shackle to slide in and out for our locking mechanism. This is our lock shackle, which will be hollow, made by aluminum, which will allow us to run a wire through the shackle, so when a robber or a thief steals the bike and cuts the shackle, the wire will be cut, allowing our system to take over and notify the user that the bike is being stolen. Here is our other enclosure for the tracker. This is currently a rough design of the enclosure. Since we're still developing our PCBs, we do not know exactly how the enclosure will look like until testing is complete.
So for the software design, there are a few features that we're going to be implementing or that we've implemented. First is the NFC authentication. Then we have the tampering detection, the GPS tracking, and the user notification. Most simplest is the NFC authentication because it requires, there aren't as many processes involved. If the correct NFC tag is used, then the lock itself is unlocked. Whereas if there is, multiple failed attempts, or if there's, if the lock is cut or anything like that, then there's a much more involved process. And we'll kind of dive a little bit more deeper into that when we discuss the bike lock activity diagram. So as you can see on the bike lock system case diagram, the system to lock and unlock for the user is much more simpler than the case states for the robber itself. The reasoning behind this is that the NFC tag will actually make things a lot simpler, at least for the controls. For the thieves or the robbers, there's a much more involved process since more information needs to go to the user, such as um, the text message that goes to the user and the location of the bike. The alarm system is also activated on the bike itself, but with the text messaging and the GPS coordinates, they both need to use the cell towers to communicate back to the database and then to the user itself. And then the GPS needs to communicate with the satellite and then the cell tower and then the user. So it's a much more involved process. To simplify things, though, if we look at the bike lock activity diagram, it kind of highlights each stage of the lock. So it shows how the components would be integrated with one another to kind of produce the response that we want. So the user would first request to unlock the bike, and to do that, they would use the NFC tag. The reader would then authenticate the NFC tag, and if it's successful, there wouldn't be any other action that's required. The bike lock would be unlocked and the system would return back to normal, waiting for the next request. However, if there are multiple failed attempts, then there are multiple states that the system would go through. And so the first is that the system would communicate to the tracker and it would turn the alarm on. Once the alarm is on, there'd be a push notification that would be sent to the user on the application where they would see that the bike lock has been tampered with, as well as the GPS coordinates. They would also be transmitted to the user. And this will help the user track where their bike is in real time. And once all of these steps have been completed, the system would then return to idle mode. And this is because the power in the system needs to be reserved so that if the bike is stolen, then the user can continue to track the bike's location by requesting its location. Um, the components in the bike lock itself will need to be in a low power mode. So there won't be any components that are actively powered on. And this is just to save power and conserve the power of the battery.
For our IDE, we chose the Arduino IDE because of its ease of use, native support for both ESP32 and Arduino MKR1500, and its extensive library ecosystem. Unlike other IDEs, Arduino IDE has a large collection of pre-existing libraries, making development faster and more efficient. One of the key reasons for using the Arduino IDE was the LTE libraries available for the Arduino MKR1500. Since our project relies on cellular connectivity for real-time alerts and tracking, leveraging these well-documented and optimized libraries ensures a stable and reliable communication system. For our database selection, we chose Firebase because of its real-time capabilities, ease of mobile integration, and low maintenance, making it ideal for IoT applications. Unlike MongoDB, which is better suited for bulk data storage and retrieval, Firebase operates as a real-time database, allowing instant synchronization of bike status, GPS location, and alerts across devices. This ensures that users receive updates immediately when their bike is locked, unlocked, or tampered with. For our mobile app software, we chose Dunkable because of its ease of use, built-in Firebase integration, and real-time testing capabilities. Unlike Flutter and Xcode, which require extensive coding, Dunkable allows for fast prototyping with pre-built components, making it ideal for IoT applications. Since cross-platform support was essential, Xcode wasn't a viable option as it is limited to the Apple ecosystem, while Flutter offers more customizable and higher performance. Its added complexity wasn't necessary for our needs. Dunkable's seamless Firebase integration ensures smooth communication between the lock and mobile app, making it the best choice for our project. Here are some screenshots from our mobile app that we've been developing, which we have a login screen, lock status page, location tracking, and settings.
So for the prototyping and testing, as far as the hardware goes, we've built all 6 of our PCBs, and 5 out of those 6 PCBs are fully functional. The ESP32 PCB and the NFC controller are fully integrated and fully functional to where they can work as one PCB. And as you can see on the top right corner of the screen, there is the first 3D printed design of the lock mechanism itself. Some of the difficulties we did have especially on the ESP32 board, is that the serial communication success rate for programming was about 90%. As we had some failed programming attempts when we were trying to upload or flash the ESP32. And we just think that missing a pull down resistor, so once we add that in, hopefully it fixes the issue. As far as the reset and boot push buttons, they're not working as they're intended to. So the proposed fix for that is smaller debouncing capacitors, and hopefully that'll also fix the problem that we're having. So the software progress for our prototyping and testing, we're still working on integrating all of the components together on the PCBs, since we only recently completed building and testing the different PCBs. As far as the mobile application goes, it's almost operational, as Russell discussed earlier. For our database itself, we're able to efficiently handle the data that's being stored on it, and we're able to send messages to the user's phone, and so that's also been successfully implemented.
Our budget for this project is roughly $800. Most of that money will go towards the PCB and electrical side of things, as the cost of the main hardware and multiple PCBs can add up very quickly. About $200 will go to the batteries, charging protection, voltage regulators, and other things related to the power supplies. We're giving ourselves a lot of wiggle room here in case there are issues like burnt regulators or damaged boards later on. For making the enclosures, we're giving ourselves about an $80 limit, as we will require a few metal shackles for both testing and practical use. And 3D printing material is relatively inexpensive, so there's not too much of a concern here. We've also set a limit of $40 for cellular provider bills, but we do not expect to go over this since it costs 3 cents per megabyte of data and 19 cents per outbound text. For our work distribution, this is a simplified table describing each other's role in this project. For hardware, Andres and I have been in charge of the PCB designs, where Andres has focused more on the locking system and power distribution, and I have worked more on the tracking system as well as the wireless communication integration. Derek and Russell have been working on the software side, where Derek has mainly been working on the locking system, motor controls, and the Bluetooth connection, and Russell has been working more on the tracking system, mobile app development, and the database. We are happy to say that after a lot of work, we have passed the halfway mark on completing our final prototype. As of now, we have the majority of our boards working and hardware testing is almost finished. The app and database are approaching their halfway mark as well. However, there still is work to be done. Overall hardware and software integration still needs to take place, as well as final enclosure designs need to be assembled. We're hoping by next week we can continue testing our ESP32 board and hopefully fix our current design flaws. The week after that, we're hoping that our final iterations of any PCBs arrive in the mail and are built shortly after. On the week of March 8th, we hope to have our enclosure designs finalized and in our hands for testing. On the week of March 16th, we hope to have all of our PCBs and software finalized so we can then begin our final testing phase. We hope that by the week of March 30th, we have finalized testing and can then prepare for the demo day. Thank you for watching our critical design review for Cycle Sentry. We hope you found something interesting about our design and project, and we'd love to hear your thoughts as well as anything you think we can improve on before our final demo. Take care.